Hi, everyone, and welcome to today's MRSOnDemand webinar, which is part of a month-long celebration of the 10th anniversary of MRS Communications. We're going to turn things over to Rigoberto Advincula, the editor-in-chief of MRS Communications, in just a moment. My name is Bob Brockler. I'm the digital media manager at the Materials Research Society. We are pleased to be teaming with MRS Communications to bring you today's event. Today's webinar is being recorded, and it'll be archived at mrs.org/webinars within a week. Today's event is the first of two webinars presenting work that celebrates the journal's 10 years of publication. Next Friday, part two of this event will feature a talk from Zhenan Bao of Stanford University on skin-inspired sensors and electronics, as well as a talk from Keith Brown of Boston University on autonomous researchers for hierarchical materials. You're looking at a list of our upcoming MRSOnDemand webinars. These are some career development types of things that we have coming up. Tomorrow, we'll co-present a rebroadcast of an ACS webinar on face masks. On Tuesday, we have an important session on banning imposter syndrome. And October 16th, we'll team with ACS once again to present working safely with nanomaterials. You can sign up for any of these webinars at mrs.org/webinars. We also have a number of great events coming up on technical topics, including the second of these MRS Communications lectures. Ellen, if you could just put a note in the chat for a second to make sure that my audio is coming through. So we have a couple of great events coming up on technical topics. Awesome, thank you very much. Including the second of these MRS communication events on the 16th. We have machine learning for microstructural data on the 21st, advanced diagnostic tools for characterizing lithium metal and solid state batteries on the 27th, and then functional materials and devices by self-assembly on the 28th. Then we're going to round out October with the final MRS communications event on the 30th, which is going to be a panel discussion with Rich Faya, Alan Taub, and Abe Lee. Registration for the 2020 MRS virtual spring and fall meeting is now open. We are really working very hard behind the scenes to make sure that this upcoming virtual meeting is a complete and a meaningful meeting experience for our materials community. You can find out details about the virtual meeting at mrs.org/springfall2020. We'll get started in just a moment, but first a couple of quick notes about the format of today's event and the webinar player that you're now viewing it in. We have two talks today. We're going to play Dr. DeSimone's talk first, after which he'll be taking your questions. Then we'll move into Dr. Gu's talk and a Q&A with her as well. By now, you've likely discovered the chat room at the bottom of the screen. Somebody just sent me a message to say you can hear me, which is good to know. It's kind of a weird thing conducting these webinars on Zoom. I can't see my control panel at all, so I'm just crossing my fingers and hoping that everything's going well. So please feel free to use the chat room throughout today's event. An MRS staffer will be monitoring that chat in case you have any technical questions. However, for the questions for our two speakers, we ask that you not use that chat room. Instead, there's a Q&A icon at the bottom of your webinar player. Please use that to enter your questions. It's much easier for us to track the incoming questions if you use that Q&A function. We're going to try and get to as many of your questions as we can today following each of the presentations. We've enabled the upvote functionality, so please do use that to ensure that the most relevant questions get bumped to the top of the queue. Our host today, Rigoberto Advincula, is the Governor's Chair of Advanced and Nanostructured Materials at the University of Tennessee and Oak Ridge National Laboratory. His areas of research include utilizing the structure and functionalities of materials on a near-atomic scale, characterizing and developing new materials, sensors, optics, biotechnology, biomedicine, energy production, and advanced manufacturing. Dr. Advincula has served as the editor-in-chief of MRS Communications since 2017, and as of the time that we signed on, I think he was having some technical difficulties. I don't think we have him on the line. So instead, I will turn this webinar over to my colleague, Ellen Crocht of the Materials Research Society.
Hello, everyone. Thank you very much for joining us. We want to welcome you to this outstanding series given in celebration of MRS Communications' 10th anniversary. One of the journal's contributions to the Society has been the MRS Communications Lecture, begun in 2016. Today's lecture by Grace Gu is the latest example of that honor, recognizing excellence in materials research through work published in the journal. We want to say congratulations to Dr. Gu. But first, we will hear from Dr. Joseph M. DeSimone at Stanford University. And let me just switch screens to give him a proper introduction. Dr. DeSimone joined Stanford after a 30-year career at the University of North Carolina. He has made significant breakthroughs in green chemistry, medical devices, nanotechnology, and 3D printing. He has authored more than 370 publications with 42,000 citations and is an inventor on more than 200 patents. He has co-founded several companies, including Liquidia, you can see, at NASDAQ, that is LQDA, and Carbon. DeSimone received the Presidential Green Chemistry Challenge Award, the Heinz Award, Lemelson MIT Prize, the 2019 EY Entrepreneur of the Year Award, and the National Medal of Technology and Innovation. He is one of only 25 individuals elected to all 3 U.S. national academies, the National Academy of Sciences, Medicine, and Engineering. And while I have your attention, let me quickly just give you a little bit of a bio on Grace Gu. She is the recipient, as I said, of the 2020 MRS Communications Lecture and is an assistant professor of mechanical engineering at University of California, Berkeley. Dr. Gu holds a BS in mechanical engineering from the University of Michigan and a master's and a PhD in mechanical engineering from MIT. Her research interests include composites, additive manufacturing, fracture mechanics, topology optimization, machine learning, finite element analysis, and bio-inspired materials. So with our panelists, our lecturers introduced, let me now turn it over to Bob, who will play Dr. DeSimone's lecture, and after that, you will be able to ask him your questions. Thank you.
First of all, let me thank the organizers for including me in this session. And what I'll share with you is our work thinking about digital manufacturing and where things are going, I think, from our perspective in transitioning from prototyping to manufacturing. And it's interesting when you think about polymer manufacturing over the years and how much it's rooted on century-old or millennia-old technologies where molding was established a long time ago, where you heat up a material into a liquid state and you pour that into a cavity of a predefined shape, and that liquid will volume fill the cavity, wet every nook and cranny, and when the liquid cools, solidifies, you have to have the symmetry to open up the cavity to release the part. And amazingly, this is still the way a lot of polymer parts are made today. The cavities got increasingly sophisticated. The injection molding tools are fairly sophisticated now, especially when you have undercuts or threads, and the tools themselves are machines. They have sliders and the like, and automatic injection systems, and this allows you to make fairly complicated parts, but still it's very limited in the geometry that one can mold. It's very limiting to get your hands on these injection molding machines. You put a lot of time and money, and it's not uncommon for an injection molding machine to make like a high cavity, tall cavity injection molding machine for electrical connectors that costs $1 million just for making 8 connectors at a time. And once you have these machines, you don't want to touch them because you just invested almost a year or more in the tool itself and spent a lot of money. And so in many ways, that investment in a new generation is an inhibitor to innovation because you're already locked in. And the magnitude of this problem is huge. The manufacturing is a $12 trillion marketplace, and polymeric products is 1.1 trillion of that. And 30% of that's injection molded, right? So this is 30%, $300 billion of the economy that's predicated on an analog molding technology that has history a long time ago. And so people have been talking about 3D printing for quite a long time, as you know, and talk about all the advantages for complexity and zero lead time and the like. But it really hasn't taken off in any significant way. The 3D printing industry is an $8 billion industry, and that includes the machines, the printers, the resins, the software, the parts. And the principal reason why it hasn't taken off is because I think basically 3D printing is a misnomer. It's actually 2D printing over and over and over again, and it's got its legacy in a mechanical engineering approach to printing, which has really gotten us very far, but it hasn't put us over the goal line regarding manufacturing. In addition to being really slow, the layer by layer approach leads to anisotropy in the parts themselves due to the orientation of the layers relative to the part. Those layers, or if it's a powder fusion technology, they're not fully fused, especially for polymers where the properties of a polymer are all derived from chain entanglements, and having, just relying on diffusion, quiescent diffusion without any convection doesn't give rise to the full envelope of entanglements that you like to have between particles or layers that you have under traditional manufacturing. And the material choices have been far too limited. And so for all these reasons, 3D printing has been pretty much relegated to a prototyping only approach. And so we came at this with a renewed interest to think differently. And as chemists, we think a lot about growing things instead of printing things, like growing crystals and the like. And we came at this with an approach that I basically think of as a software-controlled chemical reaction to grow parts. And the key technology is a DLP-based approach where we're using light at 385 nanometers, that it's illuminating a reservoir from underneath using the light. At the bottom of this reservoir of liquid, there's a very special window. And the window is not only optically transparent, but it's also highly permeable to oxygen. And so what happens is when this platform lowers into this reservoir, and maybe it gets within 100 microns of the window and you start to illuminate, that very first layer bonds to the platform, but doesn't bond to the window because oxygen is coming through the window, and oxygen inhibits the photochemistry that the light is triggering. And so we have an asymmetry right in the beginning where the part bonds to the platform and not the window. And so as you begin to lift up the part, resin can flow in underneath it. Now, what kind of window does this? And it's typically a fluorinated material. And we began studying fluoropolymers a long time ago. And these materials are, you can make an amorphous form of Teflon that is optically transparent, 385 nanometers, is highly permeable to oxygen, is very chemically resistant, thermally stable, photochemically stable, and mechanically strong because there's lots of forces on the part. And you don't want to have a lot of forces for your window, and if the windows are liquids, they get all consumed into the resin itself. And so the idea of having a rigid, solid window gives you a really great platform with which to build things. And so this is an example of the process itself. This is a platform lowering into a resin reservoir with that very special window at the bottom. We'll get really close to the window, and then you'll see the light turn on. And the light is going through a two-dimensional image as a movie. And the part will bond to the platform shown in black. And as it pulls the part up, this is, it's really just coming right off the window, it looks like. But what's happening is that there's a gap in the window, right at the window, that allows resin to flow in underneath it as you're pulling up the part to make the object that's shown on the left. And so this allows you to make things mold-free using just light, patterned light, in a two-dimensional form that allows you to make really complicated things that are actually unmoldable in any way. And so this is what we call CLIP, continuous liquid interface production, or digital light synthesis. And this is an actual image of a build surface. This is something called optical coherence tomography. It's a really powerful tool to allow you to see what's happening. But the part is bonded to the platform and gets pulled up. And as it gets pulled up, what you can see is that there's a reservoir that's uncured, or a channel that's uncured underneath the part that allows a river of resin to come in underneath the part. And that river of resin becomes a conduit for resin renewal without having to have to delaminate it off the surface. And so it's a breakthrough. It's a chemical renewal approach as opposed to a mechanical engineering approach to bring fresh resin into the build area. This allows you to go really fast. You avoid the layer by layer approach, and we can print 100 to 1,000 times faster than traditional approaches when you're operating in this continuous mode. And so we've worked out a lot of details of this. This is a generic concentration axis shown here, and we're going from the surface of the window up into the reservoir. And what you can see here, as light enters the reservoir from underneath, the intensity of light is the highest right at the interface with the window, and then it tails off as you go into the resin just due to molar absorptivity. That light is triggering a decomposition of an initiator that generates radicals, and so the radical concentration basically tracks with the light concentration. Those radicals can do one of two things. It can initiate a polymerization, but if there's any oxygen present, the rate constant for quenching of that radical is way greater than the initiation of a polymerization. And so what happens is, until the oxygen concentration gets below a certain level, there's no reaction. And then once the oxygen concentration drops below that level, then you have the forward polymerization where you get bond conversion, viscosity goes through the roof. And that gap, this distance, is really the definition of the dead zone. And so we've measured this out in quite great detail under a lot of different conditions, a lot of different resins, and the dead zone thickness as a function of light intensity. When there's no oxygen, there's no dead zone. If you have air coming through the window at low light intensities, the dead zone could be 80 microns, stripped down to 20 microns. Replace air with pure oxygen, you grow the dead zone. The other thing we need to control is how far the light will penetrate into the resin. We control that by controlling the optical density of the resin at this wavelength using dyes, and really tighten up the volume fraction, the voxel, if you will, between the X, Y, and the Z axis using oxygen, understanding the oxygen concentration, the light using dyes to control the light, and the physics of the XY pixel size. And so with that, you can imagine that every resin's different. Its molar absorptivity is different, its reactivity is different. The grain strength of the part, there's lots of forces on the part if you have overhangs and the like, and so we've got to be careful to control that. And the cross-sectional area changes dramatically depending on what you're building at any given instant, because you have to wait, for the liquid to get to the deepest pixel at that given cross-section. And so basically what's happening is there's a lot of software that, the rate of reaction and rate of building changes dynamically depending on the size and shape and cross-section and the like. And so we had to get the human out of the middle of this process. I think of this as a software-controlled chemical reaction to grow parts. And we do finite element analysis and other things to bring together a great detail to understand the simulation of the process where we have reaction kinetics, we have heat transfer, we have mass transfer, with the FEA, the mechanics of the part, all coming together to help us build these parts. And what happens is you get to see that you got parts that, with 100% UV curable systems grown continuously, the parts are isotropic. There's no detection of residual layers in a traditional layer approach. As a result, the mechanical properties are invariant with the orientation of the part. And then the key thing is not only printing fast, but you also have to get great mechanical properties. And so we realize that 100% UV curable chemistry alone is not going to get you the parts that you want, because it's hard to get to the high chain entanglement or high molecular weight between entanglements that you really want in a polymerization. So our approach for doing this, Jason and the team and Matt and others in our team and Marie really developed a process we call dual cure resin. So we basically have we combine reactive liquids, and think about your favorite epoxy where you have a diapoxide and a diamine coming together, but we also combine that with UV curable chemistry. Reactive liquids themselves are typically not UV cured, they're just reactive, give great materials. Most people in 3D printing never went down the reactive liquid approach because their printers were too slow. Because we're printing really fast, we thought we can get into this chemistry, but we also needed to make them reactive with light. We call that dual cure. This is a generic approach for doing that, where we basically take advantage of orthogonal chemistry, free radically polymerized system shown here with a dimethacrylate approach, having a system of photoinitiator to polymerize that, but also combining this with diepoxides and diamines so that when light hits it, we can set the shape with light, but then we have this latent chemistry and basically do a solid state polymerization in the form of the part to generate our particular part with very good properties. And with that, you can make amazing materials with a wide range of properties, including rigid materials with great ductility and high strength and high glass transition temperature, heat deflection temperatures. And you can see materials here that start looking a lot like ABS polycarbonate in their performance and going well beyond polyamide, brittle polyamide powders that get sintered, can fracture. These show great ductility. We have materials with a 4 gigapascal modulus that have a heat deflection temperature of 230 degrees Celsius, gets into all sorts of really high performance applications in heat exchangers. And then we have a lot of materials and opportunities in elastomers. Elastomers that have multiple different types, or elastomers that have high energy return, or materials that are high damping. And so whether you're making a running shoe where you want that energy return, or maybe a football helmet where you want the energy dissipated, between geometry and intrinsic material properties, you can really make things that are hard to make otherwise. And so the point is that all this comes together as we now have UV curable materials that can print really fast, but have the properties to be competitive or exceed the properties of conventional materials that the polymer industry has been using for the last 30 or 40 years. And so that sets a stage for now a digital future where you can combine all these characteristics into one. And so we now have a wide range of resins that fit a wide range of applications depending on what it is you want to do. We have over 50 different resins available. And you can now combine that with the hardware and 100% smart hardware that's actually can get over-the-air software upgrades and can be improved over time. And we typically add new features every 6 to 8 weeks that attenuate the build process, makes better parts, faster parts, and the like. And you can put all this together into a factory of the future and line up all the different unit operations necessary for a high throughput type of manufacturing, including solvent-free post-processing where parts get spun in a centrifuge. Instead of washing, save money, you save waste, eliminate waste. I think of every part as being alive. Every part's got its own unique digital matrix, data matrix. And in every step of the manufacturing process is streaming new information to that record in the cloud, populating it with born-on conditions, which printer, which file, which resin, which operator, which location. All sorts of mechanical property testing goes into that record, even post-market surveillance kinds of things. So really opens up a digital future that integrates hardware, materials, and software into a process that's very competitive from a manufacturing point of view with materials that have properties of a finished part. And this all comes together, and what I think it really does for us now is that it helps designers and engineers make what they need, challenge what's acceptable in designs, and create extraordinary products. And let me just play a video here.
We salute all those who believe good enough is never good or enough. Those who pursue excellence for themselves and for our planet. At Carbon, we apply our craft using science and technology to push limits and realize products unmatched in performance. Our difference is one you feel, and it is light years ahead of anything else out there. You feel it in running shoes that control energy with every stride. Saddles that enhance your performance and comfort mile after mile. Helmets that increase your protection every time you take the field. Clear aligners and dentures that improve oral health and give you more than a few reasons to smile. Crafted by Carbon is a promise. It stands for dedication and focus to crafting what you and our planet truly need. Ongoing creation of amazing answers to our toughest questions. We salute the leaders, dreamers, and doers who keep creation in motion, who boldly imagine a brighter future and craft it every day.
And so, this becomes a technology platform that's got utility in a whole host of industry sectors. And it's really a combination of having the right materials, and the right throughput and making extraordinary products. And just to walk you through some examples, you saw the Adidas running shoes, lots of different examples, different materials, different designs, offering different levels of performance. And we're real excited. This is a big market opportunity and one that we've been at for a long time with our partner Adidas, and it's gone extremely well and continues to scale with some of the new designs that just came out, different color midsoles and the like, different designs. Bike saddles is really an extraordinary opportunity, really performance driven. You can get 20% less maximum pressure on the sit bones than you can get out of foam products. And this is having a lattice that can dissipate energy, allows blood flow and for soft tissue, and really enhancing the comfort of riders. Extraordinary products that are really exciting to think about. We have the very first example of 3D printed parts on new cars coming out of Detroit. A lot of parts on a lot of big partnership with the Ford Motor Company, and parts that took 2 years to get through the Ford quality standards to get the throughput that's necessary and the performance. And really, our EPX 82 materials replacing a 30% glass-filled polybutylene terephthalate resin. Parts on cars with Lamborghini, including some very large parts made even customer-facing at this air duct right in the center of a high-performance vehicle from Lamborghini. Connectors, making connectors that have designs that in fact are unmoldable. So they actually have better products. They have 50% better terminal retention. 90% of the warranty issues in cars are failures from connectors and electrical in nature. And so we can really play a big role there. And think about all sorts of complex structures and lattices and the like that give rise to high surface area heat exchangers in microfluidic-like devices. But all of this is going to what's happening when you go digital. And instead of the traditional approach where you design in your favorite software, then when you go from bits to atoms, you're prototyping in a technology that's not your scaled up technology, it's not your scaled up material. You do all that because you got to go to tooling because it's an expensive process and you don't want to screw that up before you go to manufacturing. What our customers are doing are disintermediating the product development cycle, and they're designing products on the means of production, skipping 2 steps. And when you skip those 2 steps, it allows product teams to go way faster and do things that are quite extraordinary. And nothing was better example of that than what we faced with the COVID response, and being able to take this installed base of printers and resins and allow customers to design PPE and face shields. They're really extraordinary opportunity. Also nasopharyngeal test swabs from Resolution Medical, and designing products that really fulfilled an immediate need, introducing a new medical product in just 20 days during this pandemic, and completing over a 400 patient clinical trial at Stanford, non-inferiority trial with these advanced designs. So that's the extraordinary opportunity of digital manufacturing. The other thing I will put into context is when you go digital, this allows one to scale bespoke products where it's just an N of 1, but you're doing it for the masses. And I think what everyone needs to realize is that scanning is now almost free. And this is just the beginning of a data-driven bespoke product opportunity where customer usage is driving the opportunity, or consumer usage. There's a proliferation opportunities in medicine where there's Invisalign-like software treatment planning, driven by data. And, we do this with Riddell, where, this is me getting my head scanned, reliving the glory days of high school football. But, the best football helmet is a perfectly fitted football helmet with these kinds of lattices. And so we've got lots of players now that had their head scanned and they're wearing personalized helmets going forward. And it's now the #1 football helmet offered today. You see the same sort of trend happening in dentures where there's intraoral scanning with perfectly fitted dentures where you've got really good suction forces to hold these in. This opens up going from 8 chairside visits to 1 chairside visit, lowering healthcare costs, giving people access to great oral health that may not be able to afford it. This is the world's first FDA-approved 3D printed dentures. Same thing with thermoform aligners and the like. But you also have the opportunity for other kinds of applications, including in pediatrics and cleft palate babies, and think about airways and plagiocephaly, and there are lots of opportunities for extending this going forward. So to me, this is all about the killer apps, opportunities for taking manufacturing into the digital world and scaling it, and really demonstrating the role of this going forward. And this has been an approach for us where you take the hardware, software, materials design and really wrap around a full end-to-end solution going forward into manufacturing. And so with that, I'd be happy to take any questions, but I'm a big believer in a future fabricated with light. We use light in ways that are not too dissimilar to the photolithography world in microelectronics. We're nowhere close to the wavelength of light, but light-driven manufacturing has driven Moore's law over the last 50 years for the semiconductor industry, but that's using patterned light in 2 dimensions. And what we're doing is using patterned light in 3 dimensions, and we think our opportunity is as big, if not bigger, than what's happened in photolithography. So with that, thank you very much, and be happy to answer any questions.
Great. Thank you so much for that amazing talk, Dr. DeSimone. Even though I'm not a scientist, I really got a lot out of it. I thought it was just amazing stuff. Thank you so much.
Thank you.
So we're going to start in with taking some of the audience questions here. And unfortunately, our MRS Communications Editor-in-Chief, Dr. Advincula, was unable to join us today, so I'll be asking the questions. And we'll start with this first one. Can you comment on the high area rapid printing HARP technology developed by Northwestern using fluorinated oil in exchange of the dead zone in CLIP?
Yeah, no, I've not seen any of this in myself directly, but from what I read on the papers. So fluorinated oils have a low surface energy. They also have extremely high oxygen solubility, and I think some of the characteristics of the details of operation there are derived from the fact that oxygen plays a similar role there as it does here, in that it creates a dead zone. I think having the key is a channel to flow resin in that's uncured. And in order for resin to flow in an uncured state, it can't be polymerizing. And so it's not just a surface tension issue for resin renewal. So imagine if you have a large area and you've got to get resin to flow to the deepest pixel. And as it's flowing across laterally to get to the deepest pixel at any given increment, if there's not an inhibition of the polymerization triggered by the light, then surface tension alone is not going to be what's needed. You actually need a transport mechanism, mass transfer, and oxygen provides that. And I think those issues play an important role. The other aspect is there's lots of forces on the part. As you're pulling the part up, it's kind of like having a drop of water between 2 microscope slides, and you try to pull them apart. It's hard to do that. And if your window is not rigid and you start pulling it together, you actually can deform the window. And we know that if the window is a perfluoro Teflon AF and it's a thin film, it will drum up and down as you're pulling it, and it will snap back. And it's exasperated when it's a liquid. And so in all our work, when we do optical coherence tomography, we actually see a dead zone form when the window is a perfluoropolyether because of the oxygen. We also see massive deformation of the window, leading to defect. So there's some complementary aspects about it. It's very interesting, and we like a solid rigid window. We like plenty of oxygen to give rise to a good channel for resin renewal.
Okay, thank you. We'll remind our audience that if you'd like to ask a question, please use that Q&A icon that's at the bottom of the webinar player. We have a number here in the queue, and I'll go to the next one. The optically transparent tank that is common to SLA and DLP printer is typically coated with sacrificial PDMS to prevent adhesion and fouling. Is there a sacrificial layer that is utilized in the clip process? How is the lifespan of amorphous oxygen permeable PTFE?
Yeah, which the reason we love the Teflon AF and that class of materials is that it's very optically, obviously it's optically clear, but it's photochemically stable, and it's not swollen by organics like silicones. You know, so many organics will dissolve and partition into a silicone, unless maybe it's a fluorinated organic. Perhaps that might be appropriate. But the Teflon AF is almost infinitely durable. However, you know, I think it gets damaged sometimes when people will drop a window or cut it with a spatula or something. So there is a cadence of renewal needed there, but it's not due to usage, because we've been running printers, you know, 24 hours a day, 6 days a week, and they're very durable. They often get damaged by other means, not necessarily related to the printing process directly.
Thank you. Okay, our next question is, can you comment on the strategies to improve the resolution of 3D light patterning?
Well, there's lots of opportunities. You know, we use a DLP system, so a digital micro mirror array system, and we use light at 385 nanometers. But, you know, as the DLPs get, you know, as you go to the advanced 4K chip, for example, that a lot of our TVs run from and projection systems, you're getting many more smaller mirrors in a similar area. So the resolution's going up. So the native pixel size is getting into the low single-digit microns. And so there's opportunities either through tiled light engines or, depending on the build area, you can get to really small features. And I think you could really drive this into single-digit micron resolution. And that's something I'm very actively pursuing.
Okay, our next question is, what is the lifetime and reliability of the products made using the dual cure resins?
Very durable. As you can imagine, before any products get put into commercial use by our customers, they all run through their own set of testing. And so in you know, running shoes will have a certain set of testing associated with them, automotive is pretty rigorous. You know, it took us, you know, despite having Alan Mullally on our board, it took us 2 years to get parts onto, you know, it's the first 3D printed parts on a production vehicle out of Detroit. So we've got parts on a Ford Mustang F-150 truck, but it took us 2 years to go through Ford quality standards to get that approved. So every industry has its own battery of tests. But you know, this is where the rubber meets the road, so to speak, and you can get things moving forward in that direction. But every industry is different.
Are there process and quality controls that will allow this technology for medical applications?
Yes. Well, in fact, you know, the first applications we've got going now are in medical or in dental. And I'm really excited about, you know, these FDA-approved 3D printed dentures. You know, think about the impact in healthcare, giving people a really high-quality solution to dentures. You know, there's tens of millions of Americans that cannot afford dentures. We've actually set up a nonprofit in Durham, North Carolina, with the UNC School of Dentistry to give people access that can't afford it. Yeah, the quality standards are there. And then, you know, as you go into other opportunities in vivo, drug delivery devices, other things, they'll have its own set of standards, but yes.
Our next question is shrinking due to thermal curing isotropic, and is it taken into account in the printing software?
It's not always isotropic. It's complicated. And that's why I'm so thrilled that we have a software controlled chemical reaction, because software can cure a lot of ills. And so, you know, you think about it, you know what you want in CAD, dimensionality, and you know you want the final part to come out looking like what the CAD drawing was. But that doesn't necessarily mean that's exactly what you print, right? And so after a lot of experience, what we know is that you can print something so that it comes out looking like what you started, but it goes through a transformation to accommodate volume, negative volumes of reactions and different angles of stress. And so we do see some things, but that's where software comes in and allows you to get what you want.
Okay, thank you. Our next question is, have you explored utilizing deep UV wavelengths, less than 200 nanometers? Are there fundamental limitations in decreasing wavelength? And is the photochemistry significantly more difficult?
Great questions. So we like working in the UV. We don't like working in the visible. 385 is, there's a lot of great LEDs at that wavelength. There's a lot of great photo initiators that work at that wavelength. And the optical density issue is manageable regarding how far that light will penetrate into the organic. And, as you go to some of the shorter wavelengths, the higher energy, you don't have the optical density as much. And, we need to get light into the liquid. And so depending on our resins, you don't want, aromatic groups absorbing and cutting off. And so we have to do a trade-off. And that's why we think at 385, it's been a good balance for us.
Great. The questions keep rolling in. We'll just keep going with them here. Can you comment on the printing capabilities or your printers for high strength and high stiffness materials?
Well, one of the best materials we have out there is a cyanate ester. Not a lot of polymer chemists or chemists know about cyanate esters, but if you work in the microelectronics industry, you probably do, or aerospace. So the cyanate esters is an amazing class of materials. It has a glass transition temperature of 230 degrees Celsius. It has almost a 4 gigapascal modulus. And in fact, that's been the material of choice for some components for NASA. There is these untethered autonomous vehicles circling the space station now. They use a cold gas as a thrust agent instead of combustion, and that cyanate ester in a very complicated microfluidic-like device is the control system for this amazing space vehicle. And it's because of properties like high TG, really rigid, no outgassing, that sort of thing. It's been an amazing material. So that's one example.
Okay. Next question is, what is the importance of density in composite materials?
That's a generic question it depends on the application, I would say, for sure. I'm sure density, maybe they're saying about uniformity and properties that would be important, but, density can be valuable, but density can also be a problem. And so it depends on the application, but I don't quite understand the question, but maybe happy to do it offline.
Okay, great. I will send you a list of all the questions following this, so any that you want to follow up with, you can. Sure. Look, I think we probably have time for two more, so we'll take the two that are in the queue. Are there conductive dual cure resins? Can you create structures with conductive areas surrounded by insulated areas to integrate touch bottoms and antennas into a product?
That's cool. We've done some fillers that are, get above a percolation threshold and you have electronically conductive. Some of our customers have also done electroplating to make some antennas. We've got some concepts for a multi-material 3D printing concept. Right now the printer operates with a single component, multiple chemical components, but a single material. Liquids flow in under the part as you grow the part. I think there's some opportunities to inject liquids through a part, multiple different liquids, and get into multi-material structures, which would be a lot of fun to think about in analogy to what they were just asking about.
Great. And another really interesting question just came in, so I think we'll take two more. How does FDA approval work for carbon products? Does carbon participate in the approval process?
So we work closely with our customers and also our suppliers. And so, for example, that denture-based material is developed by Dentsply Sirona, a really high quality supplier into the dental industry. And our technical teams work with their technical teams to design resins that are compatible with clip, and we work hand in hand with them. So the supply chain becomes really important, and because it's a software controlled chemical reaction, all the resins are tied to the software in the printer, And so we end up working closely with people in that regard.
All right, well, we'll take one last question. There seems to be a limitation for materials using this process, as cross-linked materials could lack ductility for some applications. In addition, these products cannot be recycled for consumer applications.
So that's not necessarily true, but there's some elements of accuracy there, but let me just unpack that a little bit. So our process uses a UV curable component and a step growth component. The UV curable component, is forming a thermoset network. It's typically on the order of a 10 to 15 volume% of the resin. The step growth part, depending on stoichiometry of the functional groups, could in fact be a linear polymer or have very high molecular weights between crosslinks. And when you get into that regime, we have really good ductility. And the RPU 130, for example, is a material that's got a very high impact strength. It's a ductile material. It looks a lot like ABS polycarbonate in its properties, way better than like an epoxy would. Now, that being said, we have the team, the chemist, Jason, and the team at Carbon have developed some amazing chemistries that are actually chemically digestible. We have what we call reversible thermosets. And in fact, we've got a dental model resin that can be that's normally thought of as a thermoset, and it's used to make Invisalign-like products. We have other customers other than Invisalign, but think about the dental model. It's typically a thermoset. It's used for 30 minutes to make an aligner, and then it's thrown away. And it weighs 10 times as much as the final product, the aligner. Well, we've built a chemistry where we can chemically digest them, turn them back to liquids, and enter the circular economy. And so with all, so chemical innovations, you can get into a reversible thermoset. We're very excited about that.
Great. Well, we have answered all the questions. Dr. DeSimone, thank you so much for taking the time to be with us today. It was fascinating.
Thank you very much. This format's worked well. Thank you.
Great. Thank you so much. All right. Well, we will now move into our next talk. So just a little bit of a preamble. MRS Communications has been in existence. It's been publishing for 10 years now. And several years ago, we established the MRS Communications Lecture, which honors work that was presented in MRS Communications within a given year. And typically that lecture is presented at the MRS Spring Meeting. And it was scheduled to be presented at our 2020 MRS Spring Meeting, and of course we all know what happened there. So we are going to present that lecture now. It is presented by Dr. Grace Gu of the University of California, Berkeley. Her talk is titled Machine Learning for Composite Materials, and just give me a second and I will get that set up and we'll get that talk playing.
I am very excited and honored to give this MRS Communications lecture. Hello, everyone. It is great to meet you virtually, and thank you for attending my presentation. Today, my talk is on the topic of artificial intelligence for materials design and additive manufacturing. We have entered an exciting new era of scientific discovery, especially in materials design, called the fourth paradigm. We started with the first paradigm that included empirical science, where we would make something and test it. And if it didn't work, we would make something else and test that. Examples include the bridges built thousands of years ago, where at this point, we didn't have much structural mechanics or fractal mechanics theory developed. Everything was mostly based on empirical trial and error processes and seeing that things work using the tools that we have. Then we started to develop the governing equations and gain physical insight into problems using theoretical science, thanks to giants in the fields. We realized that the shape of the cross-section matters, which is better known as the moment of inertia when considering bending stiffness. However, though we are able to get this beautiful critical load equation for buckling, for instance, once the beam is no longer homogeneous and has varying cross-sectional area, this equation starts to break down, and it will be very difficult to solve analytically. Another example includes stress profiles, which can be solved analytically for one hole in the plate, but once there are multiple holes at different locations, it becomes more difficult. Then emerged this third paradigm of computational science, solving these difficult problems numerically using computers. Here we can develop a simulation and model the stress profile of many holes in a plate. While this forward analysis simulation can be very useful, if we want to go just a step further and design structures, there can be a couple of challenges. and I will show them right now. Now let's just say we want to design this structure shown here using high-throughput computing by solving for all of the possibilities. And let's say we have at our disposal two different materials, and we want to know how do we distribute these two different materials spatially within these elements to mitigate the stress concentration that's caused by these holes. Stress concentration profile is actually shown here with these colors. The number of elements in this system is 1,470, and the number of combinations is therefore 2 to the power of 1,470 because we have two different materials. In this case, number of possibilities is actually greater than the number of atoms in the observable universe, making this structure very difficult to design and to compute. Now emerged this last paradigm, or the fourth paradigm, of data science, where we use data to train a model that can then learn patterns in this data to then help us to design new materials. Now, this is not to say that the fourth paradigm is capable of replacing any of the previous three paradigms. That's not actually possible. In fact, the fourth paradigm needs at least one of the previous paradigms to feed it data for this data science paradigm. Now, big data can have a lot of patterns, and sometimes it may be difficult to interpret and deal with all this data. Machine learning algorithms has been a great tool to deal with problems that have a lot of data. In the past decade, it has been widely applied to problems such as image recognition, voice recognition, and also board games like Go. And today, I would like to talk with you about how machine learning has influenced the field of materials design. And later, I will also talk about how it has influenced the field of additive manufacturing. Now, I want to talk about the difference between using data-driven techniques in the fourth paradigm, like ML, and traditional approaches to design materials. Now, the traditional approach is shown here in blue, and approach using ML is shown here in yellow. For a traditional approach to design materials, what we will start off with usually is to get inspiration from known materials. This could be from nature, this could be from mathematics. And then experts will then extract structural property relationships. And then from there, we can design new materials based on this learned knowledge from these experts, and then fabricate materials and then test the performance of these new materials. And then we can improve the designs by sort of doing this feedback loop using trial and error. Now, this other approach using ML, shown here in yellow, starts off with first defining the design space. So we have to start from somewhere. And this could be constrained by the equipment that we have, could be constrained by the manufacturing tools, by the materials that we have. And then from there, we'll generate training data. And then our ML models would then extract structural property relationships from the data that we provide the model. And so this is the key difference between these two approaches. One is that with the second approach, we took away this domain expert needed to extract these relationships. Now our models will learn these patterns to then extract these relationships. Then from there, so this is one of the main differences. And then from there, we can design new materials based on learned hidden patterns, and then also test these new materials. Now, with these new materials, there's actually a possibility to sort of take this and feed it back into our original models, and perhaps actually increase the accuracy of our models using this new training data added. And I'll actually refer to this later on in my talk as well, in more detail. In this area, I would like to highlight some of our previous work in the field. We first started this work with a simple question. Can machine learning models tell us if a material or structure is a strong or a tough material? And this could be, of course, any property that we're interested in. Specifically here, we trained a classification model to predict whether a material was a good material or a bad material for a property of interest. It was really interesting in that while we only trained the model with output of whether it was a good or bad geometry, the model is actually able to learn patterns of what good materials or geometry should look like. Now, this is a composite system and it has different colors to represent different materials. When we compared it with the top geometries from the ground truth, from finite element analysis, we found that the machine learning models can actually predict correctly many of the top 12 geometries. This is without knowing all the boundary conditions, without knowing the mechanics involved, and only knowing whether a geometry was a good geometry or not. And so this is the training data it was only given. And now we have expanded on this work and have shown how we can actually use deep learning models to predict the actual properties of various hierarchical composites rather than just classifying them as a good geometry or a bad geometry. And we have also validated our results using additive manufacturing and mechanical testing. Now, beyond predicting material properties, we have shown that it's possible if we combine principal component analysis and convolutional neural networks to predict the entire stress strain behavior of composites evaluated over the entire failure path. And so here are two curves here. This is a stress strain curve for different unit cells. Again, the different materials represent different colors represent different materials. And we can, the two curves shown here are predicted from our models and the actual. And you can see that there's quite a good correlation between the two. We have another very interesting application is to use machine learning to predict failure in materials, such as delamination composites. In this work, a machine learning model is implemented to augment the natural frequency test, allowing both localization of damage and also quantification of its severity. We were able to interpret our model and discover a phase transition for natural frequencies with different size delaminations. We have also applied ML to exotic metamaterials and predicting the deformation behavior of digital materials as well. And here we were trying to, these are specifically stimuli responsive digital materials, and we wanted to predict how do these types of materials actually deform. So we're trying to predict this deformation behavior shown here. Now, the past few research that I've been talking about focus on using finite element analysis simulations at the continuous scale. But can we also apply similar concepts to the nanoscale? And so we did this recent work on using machine learning to design nanomaterials. Here in an example that we use graphene and hydrogenated graphene, known as graphene, and showed that the mechanical properties are superior as a nanocomposite. Here we have also looked into how can we predict defects or detect for defects in graphene. Here is an unknown, let's just say we have a graphene with unknown defects shown here. And by training a model with computed thermal vibration features, we're actually able to predict. So this is predicted and this is the actual graphene with different locations for defects. We're actually able to predict with a trained model where these defects are actually located. And so a machine learning based model approach is used to detect unknown graphene defects here by discovering the hidden correlation between defect location and thermal vibration features. The proposed strategy, we believe, offers promising solutions for non-destructive evaluation of nanomaterials. Now I want to talk to you about a couple challenges in this field, and specifically has to deal with the challenges between the difference between forward analysis and forward problems and inverse problems. Many applications in ML focuses on this forward problem. So for instance, in computer vision and image recognition, what we really care about is this forward problem. And in this case, in predicting whether an image is a cat or a dog. Prediction accuracy is really important here, and our goal is to train a model to predict whether it's a dog or a cat with as high accuracy as possible. Now, in many engineering applications, we have adopted techniques from these really mature machine learning fields. For instance, in our work that I was telling you about, we wanted to do material recognition by borrowing concepts from image recognition. We wanted to predict whether a design is a good design or a bad design. Now, even in the field of material science, prediction is very important, and we can speed up our experiments or simulations by orders of magnitude. But prediction in the future is just not enough for us. We are not just satisfied with prediction. We want our models to actually be able to tell us what is the best design. Potentially, what is the toughest, strongest, and lightest material out there? So basically, given a material property, tell me the design I should go with. Now, this is actually the problem we actually want to solve. In this case, is an inverse problem. However, techniques to solve inverse problems in ML are not well developed, and I'll explain here why. If we want to solve an inverse problem, let's just try to first convert this image recognition problem shown here into an inverse problem. The question comes out to be, what is the best dog and best cat? Now, there's not many techniques, unfortunately, to answer this question because it doesn't really make much sense. However, in our field, if we convert this problem, this material recognition problem, into an inverse problem, it comes out to be, what is the best material design? Now, this is actually a very important question to us. We want our model to be able to generate for us a superior design or a superior material. As a result, there's a need to fill this missing technique in the scientific field. And I believe that inverse design can be a very promising field to pursue, and it's currently one of our research directions. Recently, we have developed a framework called Generative Inverse Design Networks, or GINs. GINs consist of two deep neural networks, shown here, and one is called the predictor, and the other one is called the designer. In the predictor, the weights and biases are the learning variables, and this is where all the training data is fed into. And these weights and biases are optimized to minimize the difference between ML predictions and ground truth. Now, in the designer, the values of the weights and biases are adopted from the predictor and are set to be constants. And the initial designs generated with values from a Gaussian distribution are fed to designer as inputs, and optimized designs, shown here, are generated as outputs based on analytical gradients calculated using backpropagation. So the goal of the designer is to maximize performance as much as possible. So it has a slightly different loss function than the predictor. Now, here I actually also have drawn this feedback loop where the optimized designs can potentially then be verified by physics-based models and can be added to the previous training data for the next iteration of training and design processes. And this idea was sort of alluded to in the beginning of my talk when I showed this figure here, where having this dual network system can really help us to explore this feedback loop, taking our newly generated data that are superior and sending it back as new training data. So the question that we have is, what happens when we take our new optimized geometries and feed it back as new training data? Now, so here are two iterations. The first iteration is shown here, and the bottom row is the second iteration. Now, in our first iteration, there's no feedback involved. We have our training samples, and then we have our generated inverse designs. And so here we have in blue our training samples, and then in orange here are our new designs. Now we're going to take, in our second iteration, which is the second row, we're going to take our newly generated designs from our designer and feed it in as new training data. And that's shown, all the data here is shown in this graph here. And as expected, we're going to see sort of two chunks of data. One chunk is very high performing. So this is ranking. So it's very high rank, very good geometries. And this is actually from our inverse designs that we fed in as new training data. And then we have our random designs from our first training set of samples. And those are the not so high performing data points. So we will see these two chunks of data start to form. And now when we go through the designer process again, now what we have is our training samples have increased because we took the inverse designs previously in the iteration and added in as new training samples. So now all of this is shown in blue. And now with our newly generated designs from our designer, we can actually get the second set of inverse designs. And you can see that some of the performances are better than the first iteration. Now, if we actually want to compare the different generations and look at more quantitative look, we'll see that we can actually build these different iterations. So this is the first iteration, the second, and then we add it onto the third. And so again, the first iteration has no feedback. And the numbers here represent the performance, and the higher the value is, the better. And we notice that when we go from the first iteration to the second iteration, the performance has a pretty good effect. But then afterwards, going from the second iteration to the third, we start to see less an effect in performance, meaning that the performance may start to converge. Now, because we notice this convergence trend, we wondered if it's possible that we can actually use this approach to determine how much training data is needed for certain problems. So here is the sort of the what we think is a pretty exciting new direction to take in this field, and potentially to help us determine how much training data is needed for our different applications. Now, how this in general will work is that we will start training with just a couple hundred of training data. This could be because your problem has just not that much data to start off with. And then from there, we can obtain a certain number of optimized designs and get the ground truth and add it back to the training data batch. And then from there, we're going to repeat this process until the mean performance of the optimized designs start to converge. And then, so because it's only going back to our idea that, our performance starts to converge when we go from, when we start to increase the number of iterations or the number of generations. So, so we think that this is a pretty interesting idea to pursue for future research. So in addition to, I discussed some of our work in designing materials. In addition to designing materials, we think that it's also very important to advance manufacturing tools to actually manufacture them. And so my last topic today will be on additive manufacturing. Additive manufacturing has made huge strides in the past decades, with all the benefits shown here in these blue circles. While this is so, many challenges remain, one of which is that parts that are printed may have undesirable imperfections that would commonly need manual trial and error process, manual and trial correction of process parameters. So how do we change these process parameters to improve the quality of these parts? Now we start to look into methods that can allow for autonomous monitoring and correction of additive manufacturing processes using ML algorithms. Now, in order to correct for issues and imperfections, we need to detect for them first. So this is our current platform that we're using, and we have added cameras to, in this case, a fused deposition modeling printer to take pictures in real time. And then we use computer vision to detect for these issues. And then we implemented a feedback loop to change process parameters and correct for such issues. So, and the camera is going to be located. I'm going to discuss sort of some of the locations of the camera depending on what kind of imperfections we are trying to detect for. Now, so this is sort of discussing how we do the real-time monitoring and refining. And here we have different examples of process parameters. And so ultimately what we're trying to understand is how do we change these process parameters such as print speed, flow rate, nozzle height to improve the quality of our parts. And so here are some examples of imperfections that may occur while you're printing. This is specifically for an FDM printer. And imperfections that may occur are such as under extrusion. So basically not enough material is coming from your nozzle, and so you see a lot of pores start to form. Over extrusion is another imperfection, and it's basically too much material is coming from your nozzle, and so you see that there are a lot of areas start to bulge out, and so the surface is not very smooth. And then we're also trying to categorize a sample that is known to be a very good quality. Now, so these imperfections are in plane. So basically taking, we have our camera, and we're taking sort of the film area in the plane of the sample. Now, this is in general how this platform works. What we're really capturing is a probability of these imperfections of these imperfections happening. So in the very beginning, you can see here, this is one sample. You can see that the sample has lots of pores. And so in general, the platform has detected that is undergoing under extrusion. And this is seen also in the probability. So our algorithm is telling us the probability of something being under extruded is quite high. And the probability of something being good quality is quite low. And then from there, we want to adjust the printing parameters. And in this case, we're adjusting flow rate because flow rate really dictates whether a sample is over extruded or under extruded. And in this case, we're going to increase flow rate. And then you can see that the sample starts to increase in the probability of it becoming a good quality and decrease in the probability it becoming that it is under extruded. And this is also seen here in this sort of, this is one part, this sharp contrast between what is a good sample and also what is a under extruded sample and also what is a good sample, good quality sample. And this is of course tuned by this flow rate process parameter. And this is a video showing how our platform works in real time. And again, we're looking at probability of something occurring. You can see that it's very high probability of being under extruded. These are the images that we're capturing. And this is like the real-time video. And so earlier it was a flow rate of 100. And because we noticed that it was under extruded, it started to increase the flow rate to correct for these issues. And then after it's increase the flow rate, you can see that the probability of the sample becoming good is starting to increase, and then the probability of being under extruded starts to decrease. And so, so this is how our platform works. And in addition to these in-plane issues, we were also looking at sort of this out-of-plane issues, such as delamination and warping. So in this case, our camera location is going to be slightly different. So it's going to be on the side, so we can look at delamination. And for delamination, it's a little slightly different from under extrusion and over extrusion. Delamination is usually dictated by this process parameter called nozzle height. So how far your nozzle is from the print bed. So you can imagine if it's very, very high, your layers will not be, won't have very good adhesion with each other. But if your nozzle is too close, then the layers will be very, very squished. So it's really trying to achieve this optimal nozzle height to prevent these issues happening in real time, and then correcting for them if they do happen. So I want to end this talk with the vision of having these design and manufacturing platforms that I talked about today. If one day we want to go to Mars, it would be very inefficient if we need to bring all the components from Earth, such as windows and columns, beams, and including vehicles. Therefore, being able to design and manufacture efficiently in these really challenging environments will become critical in the future. So hopefully, with the work in this research community that we are doing, we can get one step closer to that vision. And this is next slide is my final takeaway. I think that there are lots of study when it comes to discovering new materials and technology for the future. And what I think is really important is not to isolate these different paradigms that we talked about in the very beginning, but really having a great synergy between all these different paradigms. And I believe that having this kind of synergy and making all these paradigms kind of work together can really help to accelerate new discoveries in the future. And I would like to end with just an acknowledgement to my collaborators, to my students, and also to my funding sources. Thank you so much for your attention.
Okay, and thank you, Dr. Gu, for that talk. Amazing stuff there once again. At this time, if you would unmute your microphone and turn your camera on. And while you do that, I'll just remind everybody that this talk was presented. It was the 2020 MRS Communications Lecture. The MRS Communications Lecture Award recognizes excellence in materials research through work published in MRS Communications. And indeed, Dr. Gu did publish an article in MRS Communications, and I believe that Ellen is going to post a link to that article in the chat room any second now. And Dr. Gu has volunteered to both read and respond to the questions. So Dr. Gu, I'll turn it over to you.
Thank you so much for the nice introduction, and hello everyone. Thank you so much for attending my presentation. It's great to meet you all virtually. Of course, I wish I was actually presenting and meeting you guys all in person, but this is also great. And I want to say the questions, I'm looking over the questions in the Q&A. I'm going to answer them live. They're really good questions, so I'm super excited. So I will get started with the first one. The first question is, why do you use, how do you choose between classification and regression? So this is a good question. So I think the key is to know for your certain problem, what you're actually looking for. So typically researchers use classification if they're solving a categorical problem. So if you want to know if a geometry is a good or bad geometry, is it a tough or not tough geometry, if this image is a cat or a dog, so sort of like categorical. And then the other option is regression, and for regression problems, you know, in this case, it would be you want to actually get a value out, so like a numerical value out, knowing what is the strength of this material, what is the actual toughness of the material. So the differences, one is more categorical and one is more numerical. And so depending on the application that you are going after, that's how you would choose the type to use. So I see the next question is why use machine learning but not other optimization algorithms like genetic algorithm? So this is also a great question. So I want to say that, you know, there's all these different types of algorithms and optimization methods. Also machine learning in this category they all have their advantages and disadvantages. So starting off with, I'll just start with, I know you mentioned genetic algorithm, but I start off by talking about gradient optimization. Gradient optimization, or oftentimes used for topology optimization problems, they're really great for problems that have a lot of design variables. But sometimes these types of methods, they get stuck in a local minimum. And so there's some drawbacks. Now, if we talk about genetic algorithms, some of these genetic algorithms, because you have these mutations, these crossovers, and there's a lot of techniques to overcome this local minimum problem. But however, genetic algorithms, when there's a lot of design variables, it's very difficult to be efficient. So sometimes genetic algorithms have drawbacks of being inefficient. And I want to mention for these two methods I just talked about, if we're solving a problem that has analytical gradient, that is really great. But a lot of problems, like if you want to solve for the toughness of this material, the strength of the material, there's actually no analytical gradient. So most times you need to solve numerical gradients. And as we know in finite elements, inverting that stiffness matrix is very expensive. And so, you know, what I think is a great promise in machine learning techniques is that you can actually use backpropagation to solve for those analytical gradients. You don't have to solve for numerical gradients. And so there's this advantage I feel like that machine learning has over some other algorithms. And then there are other, you know, how do you create an objective function needed for these other algorithms? Like, let's just say I want to predict or optimize for a certain type of stress strain curve, right? So there's difficulties in creating these objective functions, and you can create these surrogate models using machine learning. That being said, you know, I think that with machine learning to design materials or optimize materials, there are also some challenges. One challenge is that there's still some knowledge gaps, right? Especially at the intersection of machine learning, mechanics, and material science. There's still a lot of questions we don't fully know how to handle. For instance, we know that typically for a test train split, you know, for computer science problems, it's about 80-20 test train split. But is this actually the best for mechanics and material science problems? We don't know. What are the best types of algorithms to use, right? How much training data do we need? How many filters do we need? What's the size of our filter? You know, there's a lot of questions, you know, that we still need to solve in this community. And I think this is a blossoming field that I hope that many of you are probably are currently studying it and hoping to study in the future. There's a lot to be done. Okay. So for inline AM and from additive manufacturing and machine learning, how are you getting a large enough data set? Yes, so so the question is, how are you getting enough data sets? Because for additive manufacturing, you need to actually capture these images. And when you're getting these images, we capture these images through sensor technologies or cameras. And so we're taking we're basically setting these process parameters, and then we're printing the part, and we have a camera that captures these real-time images. And so, basically we want to we capture enough images and we train our model, and if we get a certain level of accuracy, for testing accuracy that we're satisfied with, usually about 90%, that's when we sort of know, okay, this is probably enough training data. But of course, more data, the better. what we found sometimes was difficult is actually storage of these images, because there's thousands of images for these additive manufactured parts. So this is one challenge that we're currently trying to figure out. All right. I'll just sort of skip around. How do you choose machine learning models for different research problems? So I would say, this is a great question, and obviously there's the literature in machine learning is very overwhelming, right? We think about there's a lot of literature, and we learn about all these different algorithms out there, right? And so I'll sort of talk about the procedure that we use in my group. And when you start to look at or analyze all the different algorithms, there's really just a handful, right? So we're talking about linear regression, there is decision tree, there's random forest, there's NN, there is CNN, then there's RNN, there is clustering, there is GAN, there is Gaussian process. So there is a handful. And then when you start to focus on the problem that you're trying to solve, and let's just say your problem, you actually want to solve for material properties. You want to be able to obtain a certain value out, right? Clustering may not be the best fit. And then if you think about, does your problem have a time aspect? And if it doesn't, RNN is probably not very applicable. So then you start to do a process of elimination, and then you're probably left with 6 or 7 algorithms. And then in this case, you don't actually know there's no like super algorithm for any set of problem, right? Or a certain application. It's often thought about the no free lunch theorem, right? And so what we like to do is that we like to try all these different algorithms out and see which one works the best for our problem, because you don't actually know without trying. So I would say, that's how you would choose different, it really just depends on your problem. And I say that try out the different algorithms that actually make sense for your problem. The question is, how much data is needed to train ML models? Yeah, so I think this is of course a big challenge for this community. How do we, how much data do I need? And is this enough data, right, that we're happy with? So this is definitely something that I think that we should study in the research field. I think in general, the goal of machine learning is to learn the relationship between input and output, right? The problems that need a lot of training data is when the input and output is really hard if the relationship is very hard to obtain. For instance, if the relationship is random, completely random, no matter how much training data you have, it's not very useful. Right? So, in order to make, learning feasible in general, you have a couple of options. One is that you have a very big network and you can learn everything, right? And so you have a lot of training data. So big network, and then you have a lot of training data. And so, theoretically, you have a large network and with a lot of training data, that is big enough to describe anything. Then, this is great for your problem. However, in practice, most situations, we don't actually have that much training data. And so there's a couple of approaches that we use, and I think a couple of them mentioned in the questions below. If you have a limited amount of training data, it doesn't matter how big your neural network is. It needs to be the right size for the amount of training data that you have. So let's just say you have a limited amount of training data. What can you do? Well, the key is that you want to make input and output simpler, right? So if it's a linear relationship, great. Use linear regression will work great. However, if it's, again, completely random, it's going to be very difficult to learn. So, if you can make it simpler, that would be great. And so that's one thing I think people are trying to do with feature engineering, right? So you have your output you cannot really change. But what if I change my input a little bit? Right, so how about I change how I represent the input to make this correlation easier? So this field of feature engineering, and then there are some questions about the physics, adding physics into your model, right? So there are ways people discuss in literature adding physical constraints into your loss function. So meaning that whenever your machine learning model is making a prediction and evaluating the physical rules, you penalize it. And so this is really great field to be in as well. And lastly, I think a really exciting also a field is active learning. Basically choosing the right type of training data, right? So choosing the right type of training data to minimize the number of training data that you need. And the most important is not training data that covers the entire design space. No, it's the training data that has the most uncertainty in it. And so that's something that people are looking into. How do we add some sort of uncertainty function into our problem to help us to obtain a good amount of accuracy needed, but with less training data, right? So that's also, so there's those, physics, adding physics to your model, feature engineering, also the active learning, I think are great fields to be in if you want to look into how do you reduce the amount of training data needed for our problems. And then how do you know when you're, how do you know when you have enough training data? Well, if your testing accuracy is high, implies that probably your training accuracy is quite high. So if you're close to a reasonable testing accuracy for your application, you're probably okay. Of course, certain applications like autonomous vehicles, they need a really high accuracy, right? So you might need to really have a lot of training data and also have a big enough network that's optimized, right? All right. Okay, I will see. I see another follow-up from the first question, the dog and cat. So dog and cat are two different species, but the property of composites is nearly continuous. How to distinguish good and bad ones without introducing human intervention? Yeah, so for this question, I'm guessing you're referring to our earlier composite work. So yeah, you're right. So, so what we do is that we use physics-based models and we solve for all of the properties. Let's just say we have like 30,000 composite geometries in our system, in our training data, and we solve for all the properties of all 30,000. And so how we distinguish between good and bad, obviously this is numerical, right? Is that we say, if you're in the top, so we take all 30,000 and we rank them from the best to the worst. And then we say, if you're the best to the middle, you're termed as good. All right, and then if you're the bottom to the so the middle to the bottom, then you're termed as bad. So that's how you can distinguish it. And of course, you can have many different levels as well, but that's how you can convert this continuous property into categorical, solve potentially classification problems. All right, okay. Yeah, so I see another question about why use neural networks for material property as opposed to other methods. I talked about the differences between gradient optimization, genetic optimization. They require solving numerical gradients, and so it's really awesome using neural networks because it sort of creates this analytical gradient for you, right? So you can solve so much faster than using finite element simulations, inverting the Simpson matrix. How to generate training data in your study? Yeah, so I think it depends what type of output you're trying to obtain, right? So I'll talk about, so I mentioned earlier the additive manufacturing work that we're, we have to, in order to correct for problems, we actually have to detect for the problems first. So we added sensor technologies such as cameras, and we captured real-time images. And so, and then we're able to, from these real-time images, to train a model to then learn, okay, so what do images with over-extrusion, under-extrusion, or delamination problems actually look like? And so here, we're actually using images for our training data. And so it really just depends, what you're trying to study. In this case, it was training data obtained from experiments, right? So it's more time consuming, can be a little inefficient. You have to store all the data as well. But also a lot of our work is using, is obtaining training data from simulations, whether it is finite element simulations or molecular dynamic simulations. So there's a question about the graphene work from earlier, and for graphene, we didn't actually do the experiment to obtain the images of graphene. We obtained the training data from molecular dynamic simulations of graphene. To figure out where the defects are. And specifically, we obtain thermal vibration features.
Dr. Gu, if I could just jump in for 1 second.
Yeah.
We're at the official end of our time, but I am We can go as long as you want. If you want to keep taking questions, we can go. I just want to be mindful of your time because I know that this is all that we had you scheduled for.
Yeah, I have to probably get going soon, but I think the questions that everyone asked today are so great, and please feel free to email me, and I hope to also meet a lot of you in the future in person. So,
great, thank you. Did you want to take one or two more? Okay, you do need to wrap up. That's great. Well, I am going to email you all of the questions that we got today, so and that'll have the contact information in them as well.
Great, thank you so much, Bob.
Thank you, Dr. Gu. It was outstanding.
Thank you.
So just remind everybody that what we have been listening to was the MRS Communications Lecture for 2020. And Ellen, are you still on the line? Did you want to say a few words to wrap up? Sorry to put you on the spot there, Ellen. Well, perhaps not. Okay, so let me just share my screen here for a moment. Thank you once again to Drs. Grace Gu and Joseph DeSimone for presenting their talks today. And of course, thank you to our audience. We had a really nice crowd today with some outstanding questions. So thank you all for that. I'll remind you once again that the point of this is the celebration of the MRS Communications 10th anniversary. We hope that you all have experienced MRS Communications. We will try and get a link to that into the chat in case you haven't seen it. And there also has been we've linked to Dr. Gu's paper that was in MRS Communications that earned her the lecture award. We've linked to that a couple of times as well. So we will remind you that tomorrow, remind you that part 2 of these lectures will be next Friday, featuring talks from Jen Bao of Stanford University and Keith Brown of Boston University. We hope to see you for part 2 of this series on the 13th. Both of those, I think, will be excellent talks. And a reminder that tomorrow we have an ACS rebroadcast webinar on face masks. On October 13th, we have Banish Imposter Syndrome for Good, which really is an important session. If you're not familiar with the term imposter syndrome, that's the feeling that I think many of us get occasionally, that we may not be as good as we actually are. You know, this will cover strategies for overcoming self-doubt. On October 23rd, we have Understanding Unconscious Bias, also another extremely important topic. And that one is part of our Diversity Month series. You can register for any of these webinars at mrs.org/webinars. All of our archived webinars are at that URL as well. These are our upcoming technical webinars, including Machine Learning for Microstructural Data on the 21st and Functional Materials and Devices by Self-Assembly on the 28th. Today's webinar has been recorded. As I just mentioned, it'll be posted to our archive at mrs.org/webinars within a week. Thank you once again to our hosts and our speakers, and of course, thanks to all of you for attending.